I'll give two lectures today. The lecture consists of this slides part and the Blackboard part. And in the first part, I'll explain my motivation to study this particular model. The motivation comes from black hole. There will be a large overlap with Gerard 't Hooft's lecture. And also, I have included some very basic things in this introductory part about black holes. And I'll just show these slides for the benefit of those who is trying to study the subject from scratch. And I hope that other people don't mind wasting some 10 minutes on well-known things. The ultimate goal is to build a quantum theory of gravity. And it is well known that quantum gravity is necessary. Some new theory is necessary to describe processes at very high energies and at very small distances, like Planck scale. And also to understand the early universe. Gravity cannot be quantized by analogy with other fields due to non-renormalizability, and the theory must involve some non-locality at the Planck scale. String theory provides a solution to this non-locality problem without creating more serious problems, but string theory is rather complex, and the non-perturbative aspects have not been fully worked out. And also, I'm not a string theorist, so I cannot talk about the string theory solution. So I'll try to come up with my own solution, or actually not a solution, but a hint to the actual solution. I like toy models. I'm just playing with toys. They have fun solving such models. So the model I'm going to describe is perhaps the simplest one can get that has some similarity with gravity. And I'll explain what exactly is similar to gravity and black holes in particular. So the model is just this Hamiltonian. We may think about n sites. N is a large number. And there is a Majorana mode on each site. It's a quantum mechanics model, 0 plus 1 dimensional. There is only time and no space. All these green dots form just one blob. There is no spatial structure. Everything is connected with everything here. And these degrees of freedom are Majorana apparatus satisfying the commutation relations. This is a Hamiltonian formalism. We talk about apparatus. There is a Hilbert space whose dimension is 2 to the n over 2, the Fock space, and the Hamiltonian is this. It's fourth order in the Majoranas. Now, there are some coupling constants here. Of course, this coupling tensor is antisymmetric in all indices, and there is this factor to, it's basically a symmetry factor. Instead of using this factor, one can just say that J is smaller than K, smaller than L, smaller than M. The average value of each coupling is 0, and the average squared is given by this formula. So it's a model with disorder, actually quenched disorder. Quenched means that we first fix the coupling constants and then compute the partition function and other things. And we will assume that the distribution of those J's is Gaussian. Each J with each particular index combination is an independent Gaussian variable. And the second moment is this. Why this formula? Capital J here is just a normalization factor. It's some constant with dimension of energy. 3 factorial is a symmetry factor, and the most important thing is n cube. This is necessary to have the right large n limit, the thermodynamic scaling. A similar model was proposed by Tiffania back in 1993, and their model had SUM spins. M is another large number, different from n. And those spins had 2 body interactions. The spins can be realized using fermions. So this SUM comes from the spinor representation. I mean, each spin is in the spinor representation of SUM. And this particular model has many properties of the original model, but it's somewhat simpler. Instead of having 2 distinct parameters, m and n, there is only one parameter, capital N. So this capital N is the number of those green dots, the number of Majoranas. The green function, which is defined this way, it's a Euclidean green function. Is the same as the original Tiffania model. But disorder effects are weaker in this particular model, which makes it somewhat easier to study. And the new development is that this model, as well as the original model, of course, has an emergent conformal symmetry if beta j is much greater than 1. J is this parameter with dimension of energy, and beta is the inverse temperature. And this emergent conformal symmetry is broken, and there is a corresponding pseudo-Goldstone mode, a soft mode. A detailed calculation, I gave a series of talks at KTP regarding this model. Detailed calculations were done by Maldacena and Stanford in this paper, and by many other people. In my talk, I'll follow a recent paper with Josephine Sach. Why this model? Why study this model? Sajid and Ye were interested in strongly correlated systems at low temperatures. But my goal is to understand quantum gravity. So we may begin with the observation that the semi-classical theory of gravity works well in many cases, like Hawking radiation and black hole thermodynamics, but it also has some paradoxes. And the concrete goal is to have a fully quantum model, even a toy model, that matches the predictions of this semi-classical gravity. But since it's a well-defined model, not semi-classical, not using any approximation, we can resolve some of the paradoxes at least. We can have a definite answer to any question. And the important step is to construct a model that would be similar to a black hole. How do we do that? We need to find some universal properties of black holes. This property should be the same for all black holes, like Schwarzschild black holes, rotating black holes, charged black holes, and so on. And it should be different from systems that are not black holes. At least this property should not be trivial. It should be not so easy to satisfy. And the SYK model is an example of a model that shares this property. This property has to do with out-of-time autocorrelators, and I'll explain what that means. We will study a 0 plus 1 dimensional quantum mechanical model that is similar to dilaton gravity in 1 plus 1 dimensions. And the dilaton gravity can be regarded as the simplest example of a black hole. Here, let me begin an introduction to black holes, which many of you already know. This is the Schwarzschild metric there is a radial coordinate, time coordinate, and angular coordinates. Angular coordinates will not be used much in this description. There is an apparent singularity at r equals a at the Schwarzschild radius given by this formula. I'm using the system of units where the speed of light is 1 and the Planck constant is 1, and this is Newton's constant, g. But this apparent singularity can be removed, and in the morning lecture by Gerard Hooft, there was a nice picture how the space can be extended and a larger space can be constructed. This is a baby version of that. We can consider a Rindler patch of the Minkowski space, which has this metric, and if we are given this metric that has coordinates t and w, kappa is some parameter. It's not an independent variable. One can see w in the denominator, and one may say this metric is singular, but it's actually related by a coordinate transformation to coordinates x0 and x1. This is somewhat similar to the polar coordinates. Kappa t is like the polar angle, and square root of w is like the radial coordinate. So one can map this region of w greater than 0 in this picture to a wedge in the Minkowski space. This is called Rindler wedge. And just from this transformation of coordinates, we recover the Minkowski metric. And the same is applicable to the Schwarzschild metric. So the solution that we obtained by mapping the Schwarzschild patch to a bigger space, this wedge is known as, we can just do that. It will be a physical region where we can measure things, but we can also extend this space to a bigger space that is called an eternal black hole. We extended the physical region where this guy lives to the future and to the past. The past horizon, since on this side of the past horizon may be regarded unphysical because if the black hole forms from matter, there is matter along the past horizon. So this may be regarded unphysical. But again, we can take a formal point of view and say that the only physical thing is this wedge, and if we want to understand this property of the properties of this wedge at later times when everything has come to an equilibrium, we can do whatever we want that is consistent with the physics in this region, and we may extend the space in this direction as well in that direction. And also we can recover this wedge on the left, and in my lecture this space is different from that space. It's not identified in any way with the physical region. Now, if this guy decides to go inside the black hole, well, it's not a good idea to go to the black hole. You'll hit the singularity. But there is a point of no return when he crosses the future horizon. The important parameter of a classical black hole is the surface gravity. And this whole picture has a Killing vector that is equivalent to a time shift at infinity and a Lorentz boost near this point, the space-like horizon. And the ratio of the Lorentz boost at the space-like horizon and the time shift at infinity is called surface gravity. It's a parameter with dimension of inverse time. Now, let's go to quantum black holes. And now things become interesting. there are three levels of understanding of a quantum black hole. The first level is something well known. It's quantum fields in classical space-time. This theory was constructed by Hawking with further improvement and clarifications by Andrew and others. And the black hole with surface gravity kappa is characterized by the Hawking temperature, kappa divided by 2 pi, and also by the Bekenstein-Hawking entropy. The horizon area divided by 4, where we measure length in Planck units. This picture is nice, but it's incomplete, and it has some contradiction with quantum mechanics. And we would like to resolve those contradictions. But unfortunately, it's not so easy to do it at once. So there is some intermediate level of understanding. We can think about corrections to the Hawking picture. And the corrections come from interactions between incoming particles and the Hawking radiation particles. And this theory was constructed first by Drey and Hooft for classical particles, and you've heard about the quantum version this morning, and there is an effective action. This is a wonderful theory. I would like to focus on observable quantities that are related to this theory of interaction of incoming and outgoing radiation. Let's only think about things that are defined in the physical region. How do we know that incoming and outgoing interactions, radiations interact? We can construct this quantity called out-of-time order correlator. X, Z, Y, and W are some operators that are applied far away from the black hole, at least not at the horizon, in this physical region. And in the ADS picture, this would be operators applied at the boundary. And for sufficiently short times, this is the Schwarzschild time times the logarithm of entropy, one can calculate such things, not going to very high energies. We have to go to reasonably high energies for the following reason. When incoming and outgoing particles interact, there is a Lorentz boost that is exponential in the time delay between the incoming and outgoing things. And we have interactions at arbitrary large energies. If we just focus on interactions below the Planck scale, then we get this bound on times where this picture is applicable. Now, if calculation is done in a concrete model, such as the SYK model or in string theory, one finds some correction, some deviations from the semi-classical picture, and one can go to times slightly larger than that. But one can expect that as time increases, there will be other corrections that are not completely understood. And so I prefer to be on the safe side and say that this theory is limited to short times. Another way to characterize these interactions between incoming and outgoing radiation physically is to think about correlations in the Hawking radiation. But it turns out that if we just collect Hawking radiation over some period of time and ask whether this radiation is completely thermal or whether there are some correlations. There is an argument due to Page that we have to wait very long time until half of the black hole evaporates, and only then we'll find correlations in the radiation. But we may ask a slightly different question. Suppose the black hole doesn't exist by itself, it's entangled with another object. And these two objects form a field double. That other object can be another black hole in a different universe, or it can be a quantum computer some quantum mechanical thing, and they form a thermophile double. This interaction between incoming and outgoing radiation result in correlations between different Hawking radiation quanta and the purifying subsystem, that black hole or a quantum computer. And currently we're playing with this class of ideas and things like traversable wormholes and Haydn-Preskel decoding are related to this class of ideas. Juan Maldacena will hopefully say more about traversable black holes, thermophile doubles, and things like that. Eventually, we want to achieve a complete understanding, which would mean computing the S matrix and correlations in the Hawking radiation itself over long periods of time. From this story, we can only infer certain properties of the S matrix, but we cannot calculate the full S matrix. That requires a complete theory, and we don't have one at the moment. Now, again, this is something well known, Hawking radiation. How do we understand Hawking radiation? This is a cartoon of a black hole, and it has some temperature T, which may be low, but if we go close to the horizon and measure this temperature with respect to the local frame, if we hang a thermometer on a rope, and this thermometer is just above the horizon, it will show a pretty high temperature, arbitrary high as we approach the horizon. So we can think about many radiation quanta that are emitted by the black hole and fall back, and some of them with sufficiently long wavelength and small angular momentum make their way out of the black hole. But there is some thermal shell of radiation quanta around the black hole. So if we ignore those quanta that go out, we can say that the system is at thermal equilibrium. But how do we understand that? There are two different ways. Actually, there may be more ways, but these are the two ways I know how to derive Hawking radiation. One way is to use the Euclidean picture, where the coordinate system I showed correspond to polar coordinates. And notice that in polar coordinates, everything is periodic with period beta, which is related to the surface gravity. And another way is to use the Lorentzian picture. So we live in this wedge of space-time, the physical wedge, and if we only consider causal correlators between free fields, then it's sufficient to solve the Heisenberg equation for operators in the physical wedge. If we want to know more general correlation functions, then we need to have some data on the Cauchy surface, which is the path horizon. So if we know the initial condition, the quantum state on the path horizon, evolve it, then we'll know those correlations. And we may assume, it's an assumption, but there are some justifications of this assumption, that the fields on the path horizon are correlated exactly like in the flat space. And in the flat space, we talk about vacuum correlation. But by some magic, basically by the coordinate transformation between the Minkowski space and this Kurtz space, we get a finite temperature. So this is an example. A Majorana fermion in 1+1D, it's a chiral fermion moving to the right, has this correlator in Minkowski space. This flat horizon, path horizon can be, of course it's in a curved space, but to consider correlations exactly on this line, we may approximate it by the flat space. And if we just do this coordinate transformation, then suddenly we recover the thermal correlation function of the Majorana fermion with this temperature. There is some entanglement pattern. Each radiation quantum on this side is entangled with its partner inside the black hole. That's what this picture suggests, because we begin with a pure state on the past horizon, which includes both the region outside and inside. This is the black hole thermodynamics. Basically, we can identify thermodynamic quantities such as temperature and entropy with geometric parameters, and these are some well-known formulas. Let me skip that. How does information get out of the black hole? Now we're talking about two corrections to the Hawking picture. And again, this is something Gerard Hooft talked about this morning: incoming and outgoing radiation quantum interact. The Lorentz boost is important, and incoming quanta produce a shock wave on the past horizon, which influences the outgoing particles. However, there is a very subtle point in this picture, and I want to stress this point. If we do a physical measurement in the physical region, a physical measurement would be like something like this. We have some probe that has its own Hamiltonian. We couple it to the radiation and start with some initial state, evolve over time, and then measure the final state, measure some observable. Any measurement like that would produce the results that are predicted by Hawking, up to small corrections. There are corrections that are proportional to Newton's constant. Those corrections may accumulate over time, but before they become significant, we have to wait as long as Page's time, or maybe slightly less than that. We're talking about corrections at short times. Where do they come from? It turns out that if we consider physical measurements, we'll not see any significant corrections. All the corrections will be suppressed by a factor proportional to Newton's constant. Only out-of-time order correlations that are measured cannot be measured physically. They require evolving the black hole back in time. Only those correlators will show up corrections. And the fact that ordinary correlations do not show corrections is related to the following fact. The shock wave is actually a shift along the past horizon. But the quantum state on the past horizon is translationally invariant. If we shift it, the density matrix remains the same. To find a non-trivial effect, we need to relate things behind the horizon and above the horizon. And how is it done? Using an out-of-time order correlator. Let's read the separator and see what happens. A of 0 creates a shock wave. It propagates. And B of t is applied somewhere in this place, and we evolve it back in time. So this, the excitation created by B goes behind the past horizon. Then we apply C to get some information out. And then we apply D. And finally, when we apply D, we have to evolve this thing forward in time. But that excitation goes through a different shock wave because there is an intertwining operator C. So on the way back and on the way forward, the radiation interacts with different shock waves. And that's why there is a non-trivial effect. It's not possible to see this effect without going back in time. Of course, we cannot go back in time if we have a real black hole, but if we assume that the black hole has some Hamiltonian, we can just evolve this Hamiltonian back and forth however we like. Naturally ordered correlations, that's what I was referring to previously, when we couple a probe to the black hole radiation as given by this formula. And in the end, any measurement result is related to a correlator where times go forward and then backward. And those times are on the Keldysh contour. Out of time order correlation are on the double Keldysh contour. The important feature of out of time order correlations, not in the black holes, but basically for many systems, is that they grow exponentially in time. And that was first understood by Larkin and Ovchinnikov a long time ago. They calculated out-of-time order correlators for a single classical, semi-classical particle using commutators of two observables like P and K at different times. And using the semi-classical formula, one gets this result. So the commutator is proportional to this susceptibility of P at time t to X at time 0. And if the system is chaotic, this thing grows exponentially, and kappa is the Lyapunov exponent. Now it's the classical Lyapunov exponent of a chaotic system. And for typical non-integrable systems, now we're talking about many-body quantum systems. Those correlators also grow exponentially, and there is a prefactor that is small. It's 1 over the system size, but there is some exponential growth. Now, we're talking about out-of-time order correlators in a many-body system. It's not exactly this thing, but still there is an exponential growth. And the exponential growth saturates when this whole expression is of the order 1. The exponent kappa for a quantum system at temperature T was obtained by Schenker, Stanford, and Moldasena. It turns out that kappa is less or equal than 2 pi T. Now, we come to the universality thing. How do we characterize the black hole by some universal property? The universal property is related to the X exponent kappa. If we calculate the out-of-time order correlators related to Hooft's effect, the shock waves, by putting a black hole in a box like the anti-de Sitter space, we'll obtain some answer, and the exponent is 2 pi t exactly. There are some stringy corrections calculated by Schenker and Stanford, which makes this exponent slightly less than this expression. And most many-body system, if we pick a random many-body system, it will show an exponent much less than that. So finding a system with exactly this exponent would provide some analogy with black holes. And these are some failed attempts to fake a black hole. I went through this exercise, so you don't have to repeat it, but there may be some turns that I didn't take, and it may still be worth repeating some of these steps. So the Heisenberg model with random all-to-all interactions, these are spins, and there are random couplings. It's a bunch of spins that interact with each other. One can consider this model at high temperature or at low temperature. When the temperature is greater than the typical interaction, then the Lyapunov exponent is of the order of J, which is by definition less than T. So we're not in the universal regime, nothing similar to black holes. We would like to take temperature to 0, make it much less than J. Unfortunately, this type of system is unstable to spin glass ordering. So this system doesn't work. Another model is a random Hubbert model. It becomes a Fermi liquid at low temperature. It doesn't develop a spin glass order, but it becomes a Fermi liquid. It's a kind of boring state, almost free fermions. However, here there is a possibility to construct something interesting. The Hubbert model has some parameter, and one can look at the phase transition between the low and between the strongly coupled and weakly coupled Hubbert model. And also, people, condensed matter theorists now are studying certain regions of parameters in the Hubbert model that are related to the temperature. So the temperature is not exactly taken to zero. It remains finite with respect to a certain parameter in the Hubbert model. And that might also give some analogy with black holes. The SYK model is what I have already shown to you. It has the same green function, emergent conformal symmetry, and so on. Now, the special thing about the SYK model is this. It's strongly correlated at low temperatures, but it's not a Fermi liquid or a glass. It's exactly soluble at sufficiently low temperatures, in this regime at least. And it has emergent symmetries. The equilibrium green function has an emergent PSL-2R symmetry. It's a variant of conformal symmetry. But there is an effective action for the pseudo-Goldstone mode that has high symmetry, diff S1, which is explicitly broken. And the manifold for the pseudo-Goldstone mode is diff S1 divided by PSL-2R. And if we think what it means, it's a reparameterization of the circle. Now, I'll go through some things that I'll do in more detail on the board, but here they are. We can consider the evolution of a single Majorana modes interacting with other modes, and we may introduce an effective bath, effective field acting on this mode. It's a fermionic field defined as the derivative of the Hamiltonian. It's expressed in terms of the other Majoranas. And since there are many neighbors interacting with J, we have a Gaussian fermionic field. And one may think of each Majorana fermion living in a heat bath of other fermions with this effective field. And one can write self-consistency equations for the correlation functions. Sigma is the correlation function O. It shouldn't be O, it should be Xi. Xi is the same as O. I didn't change this. So sigma should be the correlation function of the Xi, and G is the correlation function of chi, and there are Schwinger-Dyson equations. One equation simply says that if we have a bunch of fluctuating variables chi, and we consider this combination, that then it's a Gaussian with this second moment, sigma. And this is the usual Schwinger-Dyson equation. The technical path to the solution of the model, it's a very convenient tool, replica diagonal effective action. Instead of saying that sigma is the self-energy and G is the green function, we say that there are some dynamical variables, sigma and G. At equilibrium, they are, as I said, self-energy and green function, but out of equilibrium, they're different. And we calculate the free energy using replicas. I'll go through this later, and we obtain this effective action using these dynamical variables. And stationary points of the effective action are solutions to the Schwinger-Dyson equations. A soft pseudo-Goldstone mode in the zero temperature limit, the Schwinger-Dyson equation has a time reparameterization symmetry. We can take G, which can be the green function of the dynamical variable of the previous action, and plug f of tau instead of tau. So we replace tau with f of tau, and if we replace the green function by this expression and the self-energy with this expression, they still satisfy the equation of motion, the Schwinger-Dyson equation. And therefore, the solutions to the Schwinger-Dyson equation have this form. G infinity is just the power law function, and f is an arbitrary function. It's composed of two functions. One is a map phi from the circle to the circle, and there is also an exponential map. So phi is like a deformation of the circle. We think about the circle as a spring, and phi describes the deformation of the circle. And then by using the exponential function, we map it to the complex plane. And when beta j is large, the energy of this deformed circle depends on phi in a particular way. The minimum energy is, of course, when the circle is not deformed, when we have phi proportional to tau. But in general, the effective action is given by this formula. And that is the Schwarzschild derivative. This is perhaps the nicest feature of the SYK model, that the lower energy degrees of freedom, the soft mode, is described by a very simple model using the Schwarzschild action. And the same model describes a geometric problem. If we take the hyperbolic plane, this is a picture of the hyperbolic plane, and consider, say, a balloon in the hyperbolic plane, or we may say it's a string of the some membrane on the hyperbolic plane. And its energy depends on the length and on the enclosed area. In this way, if we rewrite this expression in suitable coordinates, we'll recover this formula. This observation was extended by Moldasena, Sternfeld, and Young. They wrote this action of the balloon in the hyperbolic plane as dilaton gravity. So this is the dilaton gravity model, Jakiv-Teitelbaum model. And this model can be also considered in the Lorentzian space. In the Lorentzian space, instead of this curve, we have two curves, one on the left and one on the right. These blue sections of the curve describe an analog of that blue curve. So it's ADS2 with boundaries that are not located exactly at infinity. They cut out some space from ADS2. And a pair of boundaries is equivalent to a pair of shock waves. These are just different descriptions of the same geometry. And this comes from this paper, and I hope Juan Moldasena will say more about that. Now, I want to summarize. Some properties of black holes and the SYK models are similar. In particular, out-of-time order correlators are similar and have the same Lyapunov exponent. And in the remainder of this lecture, I'm not sure if how much I can do. I'll say something about Feynman diagrams. And in the next lecture, I'll try to cover the other topics, the effective action, emergent symmetries, and finally, the Schwarzschild action. Yeah. So maybe it's a good time for questions for this part.
Well, I have a quick question. Can you say a word about how you compute Lyapunov exponents in the Heisenberg model?
How to compute Lyapunov exponents in the Heisenberg model?
Or the model which you say didn't work, but still, how do you?
It's hard to compute. I can only give a hand-waving argument. Basically, if we're at high temperature, then everything evolves at this time scale of j to the minus 1, and the Lyapunov exponent should be of the same order. One may give a slightly different description of operator spreading. At high temperature, one can evolve an operator backward in time using the Heisenberg equation. And if this operator acts on a single spin, we apply the Heisenberg equation, And we get operators in the first order. If we do the time evolution as the exponential of the Hamiltonian in the first order, we get the commutator of the Hamiltonian with a single spin operator. It has 2 spin flips. Then we continue evolving and we'll get more like 4 spin flips, 8 spin flips, and so on. And the number of spins that are affected by such an operator grow exponentially in time. And we basically need to estimate the exponent of that growth. But technically, it's pretty difficult because these are spin operators. They have a rather complex algebra. I think it's possible to do it numerically, but difficult.
Okay, if there are no other questions, let's go on.
Yeah, thank you. So the Hamiltonian, for a slight generalization of the SYK model is this. It's, well, let me write down the usual Hamiltonian. We can generalize instead of using 4 operators. We can take Q operators. Q is any even number. And write Q factorial I to the Q. Now, I'll use Q equals 4 in all calculations. How do we solve such a model? Let's work in the Euclidean time. Let's write the Euclidean action, which is minus integral of Euclidean Lagrangian over imaginary time. And the Euclidean Lagrangian is sum over all the Majorana modes. In the first formula, the chi's are operators. Here, chi's are Grassmann variables. Then we can start with the free part. And initially ignore the Hamiltonian. So we'll be using the interaction picture. In the interaction picture, we can calculate the green function very easily. In the interaction picture, the bare green function is just described by the derivative with respect to time. It's oh, I already put -1 here. And if we invert this relation, we get -1/2 and I guess I should write the definition of the green function, because condensed matter physicists use a funny convention, and I have followed this convention from such a Tiffania paper. The green function is defined as minus this minus sign. We do not sum over j. If we want to sum over j, we should put a 1 over n factor in front. Then, starting from this, we will compute Feynman diagrams. But there is one point. When we do Feynman diagrams, or when we calculate the green function, there are two averages. One average is taken over the Grassmann variables, and the other average, the other integral, is taken over the random coupling constants. And there are two ways to do those averages. One is known as Quenched disorder. The other is annealed disorder. What do we do with the Quenched disorder? With the Quenched disorder, we fix the j's, calculate the quantity we want, like the green function, and then integrate over the j's. So let me write it down. So the integral over j comes after dividing by the partition function. And the annealed disorder is integral over so there are two different recipes, and the first is more physical. We could consider the annealed disorder, and actually I will do most calculations using the annealed disorder, and I'll show where the difficulty, where the difference is between these two expressions. So let's proceed with the calculation for the annealed disorder. We basically write Feynman diagrams and then average each diagram over the disorder. And suppose we want to calculate the green function. G is, this line is, the physical difference is this. Here, we first fix J, and then consider some physical quantity. In principle, for each realization of J, this ratio will have a definite value, and we would be able to measure this quantity for each realization individually. The integration over J is just for theoretical convenience. The anneal disorder is different. Again, we could average something for each realization of J, but each J comes with a weight that is proportional to the partition function for the given J. You see, this denominator can be called Z of J. This is the partition function. And the anneal disorder introduces an additional weight proportional to Z of J for each coupling configuration. I guess it's not very physical, but it's easy to compute in this case. So let me just write down the usual series that corresponds to the Schwinger-Dyson equation. Yeah. Right, right. It's absorbed here. Yeah. Oh. Yeah, the same probability distribution goes in both integrals. But the second integral, if we do the anneal disorder, we can write it this way. Integral over dj times z of j. The probability distribution goes here. And times this ratio. And if we cross out z of j, we'll get the Quenched disorder. So this is the usual diagrammatic series where this thing is the self-energy. And for the self-energy, we can have various diagrams. Some of them are more important than others. So let's draw some contribution to the green function. Now, let's put indices here. We have the same index on the external lines and some indices K, L, M. And each vertex corresponds to an instance of J sub JKLM. Now, we have two vertices with the same set of indices. And as we average over the disorder, integrate with the Gaussian distribution, we'll get a certain value. So essentially, we should write this thing. We have one copy of the coupling constant. Another copy of the coupling constant. And this dotted line represents the Gaussian average. And by definition, this thing, if we integrate with the Gaussian measure, we get this number. So we should put this factor in front. Maybe I'll, yeah. I guess. So when we compute the diagram on the top, we should decorate it with the dotted line. So the diagram will actually look like this. And there is a factor in front, 3 factorial j squared over n cubed. But this 3 factorial cancels with the symmetry factor, because this diagram has symmetries. So it's just this. Now, we sum over internal indices. And each sum gives n, which cancels with this n cubed. This is important. This is how the thermodynamic scaling appears. So in the end, we get just g squared g okay. So the important thing here is the cancellation of n cubed. We can consider other diagrams and see whether all the factors of n cancel or not. And let me draw some diagrams where the factors of n cancel. Those diagrams are called Malonic. I don't know why they are called that, but anyway. Such diagrams can be constructed recursively. We start with a simple diagram, and then we can insert the same pattern in here or in both places, anywhere in this picture. So there is this diagram. This diagram, for example. This diagram, and so on. So there is a bunch of diagrams, and in each such diagram, factors of n cancel. Now, one can notice that inserting those extra things is equivalent to replacing each line with the full green function. And that gives the Schwinger-Dyson equation. This gives the self-energy in the Schwinger-Dyson equation. Sigma of tau 1, tau 2 here it's the full sigma, whereas in this equation, it's the bare green function. So this will be full green functions and decorated with a dotted line. Yeah, thank you, G cube. And this should be combined with the standard Schwinger-Dyson equation. And this system of equations can be solved. And one gets at zero temperature G of tau 0 equals minus B to the delta. I'll explain what B and delta are. Maybe I'll put tau 1, tau 2. Q is the number in the definition of the model, the number of Majorana fermions interacting with each other. And B is given by some expression with little physical meaning. Just some numerical factor. So this is the zero temperature solution, and it's obtained in the following way. This bare green function is minus the time derivative. So it's proportional to the frequency. And at low frequencies, at long times, this term may be neglected. So here we're making a leap from perturbation theory to something non-perturbative, because when we do this diagrammatic expansion, formally it has a finite convergence radius. But instead of restricting ourselves to the convergent disk, we write down the Schwinger-Dyson equation and solve it. And we obtain a solution that is valid beyond the convergent radius. The convergence is in terms of the inverse temperature. So that previous solution works, the diagrammatic expansion converges at high temperature, but we can still use it at low temperatures. And in particular at T equals 0. Okay. So this is neglecting d tau. And assuming that tau 1 minus tau 2 is much greater than j to the minus 1. Later, I'll show you the finite temperature solution. But now, let's focus on powers of n. In principle, we should care about two parameters. One is beta j. Beta is the inverse temperature. And the other is n. These are two large parameters. And right now, let's just assume that n is much greater than 1 and not specify beta j. Later on, we will consider special properties when beta j is large. Actually, this is one property that requires that beta j is large, because that solution was for a 0 temperature, where it is infinite. So in the green function, these are the important terms, the Malonic diagrams that give the Schwinder-Dyson equation. What about high-order correlators? Which diagrams are important for high-order correlators? Let's consider the 4-point function. And that's called f of tau 1, tau 2, tau 3, tau 4 multiplied by n. And you'll see, oh, sorry, no. This is too quick. Let's just consider this quantity and see what diagrams contribute to it. One diagram is this. It's tau 1, tau 2, tau 3, tau 4. Plus other diagrams. And other diagrams will be suppressed by a factor of 1 over n. So let's write n f of tau 1, tau 2, tau 3, tau 4. This expression is just the sum of all other diagrams. Let's write down some diagram and see what it gives. This diagram, for example. Now, we should remember that the indices here are jj, and the indices there are kk. And we're summing over j. We should sum over intermediate indices, but there are no intermediate indices here. So this diagram gives us the factor delta jk. So if we average the original function over all j's and k's, let's this diagram will give us 1 over n factor after averaging. So it is suppressed in 1 over n. But this 1 over n factor will not be present in F because by definition it cancels with this. Now, let's consider some other diagram. It's sum over L and M. And this gives the factor n to the minus 3. Each dotted line gives n to the minus 3. And the index summation gives n squared. So this diagram is of the same order of magnitude as that diagram. And as a result, we get the following. F so it's a sum of letters. Each letter is proportional to 1 over n. One can also include other diagrams, but one can check that only letters have 1 over n, and other diagrams have a higher power of 1 over n. So this is an important result. And also, we should include diagrams that are different by the permutation of 3 and 4. The next thing, it will be probably the last thing today. I want to describe the difference between anneal disorder and Quenched disorder again in the diagrammatic language. So to do the Quenched disorder, we can first do the anneal disorder as described here. Basically, all the calculations are related to the anneal disorder. And then we can use the replica trick. So the replica trick is this. Suppose we want to compute the partition energy, or the partition function, or the free energy. This is slightly easier than computing a correlation function. We actually want to compute minus log z averaged over disorder. And we write it formally like this. So we compute z to the m, average it over disorder, not computing z, averaging it and raising to the power m. And to compute z to the m, for integer m, we can introduce m replicas, m copies of the system. So now, we can also do the following thing. We can put a logarithm here. This will look like the calculation of the usual free energy with m copies. And so when we calculate the log of Zm, we should consider all connected diagrams as usual. So it's a calculation of the free energy with m copies of the system, and as usual, we consider connected diagrams. But each diagram will get some weight depending on the number of replicas. So let's see what happens. Suppose we have some diagram that contributes to the free energy. And this is one diagram, and this is another diagram. In the usual scheme, each fermionic line carries index j, which refers to a particular Majorana mode. But it also carries a replica index because we have m copies of the system. And the coupling constant is the same for all replicas, but the fermionic propagator is diagonal in replicas. So in this case, the fact that the fermionic propagator is diagonal in replicas enforces that this must be the same index alpha. In this diagram, we can have J alpha, K alpha, L alpha, and let me draw it bigger. alpha can be different from beta. Although each fermionic propagator is diagonal in replicas, this dotted line represents the disorder average, and we use the same couplings for each replica. Therefore, we may have one part of the diagram belonging to one replica and the other belonging to the other replica. Now, this diagram scales as m, and this diagram scales as m squared. When we consider this limit, in this case, m cancels. And in that case, we divide by m, it just get m. And as m is taken to 0, the second diagram vanishes. So the conclusion is that in the Quenched disorder calculation, we should only include diagrams that are connected along fermionic lines. And this diagram excluded from the Quenched disorder calculation. The excluded diagram happens to have an extra factor of 1 over n squared compared to this diagram. This is happens to be proportional to, oh, I forgot the fourth line. There should be 4 lines here. This happens to be proportional to m times n, and factor of m cancels, and the free energy is proportional to n, that is, the free energy is extensive. And here, it is proportional to m squared times n times n to the minus 2. So the diagram that is excluded in the Quenched disorder calculation is proportional to n to the minus 2. And that's why, for the most part, one can ignore the difference between the annealed and Quenched disorder. This is a special feature of this model that was not present in the original Tiffania model. The difference between the Quenched and annealed disorder is rather small. It's proportional to n to the minus q minus 1. And I guess it's time to conclude. We have identified the important diagrams for the green function. These are the Malonic diagrams. For the 4-point function, there is one leading contribution and a bunch of subleading contributions which are given by ladders. And for higher order correlation functions, one can identify the leading diagrams also. They correspond to kind of 3-level interactions between ladders. Yeah, that's it for today. Thank you for your attention.